Okay, so let's continue with some examples here. Now, the probability of odd plus even, we intuitively know is 1/2 plus 1/2 equals 1. That illustrates the first probability rule. So nothing difficult there. However, I'd like to just focus in on the rules. And let's do probability of odd. And rather than use our intuition, let's focus on the rules. How do I get odd? Well, it could be 1 or 3 or 5. Okay? Well, to get that, then we can use the OR rule for mutually exclusive events and get the probability of 1 plus the probability of 3 plus the probability of 5. There's no overlaps, so they all simply add. Now that's 1/6 plus 1/6 plus 1/6, which is 3/6 or 1/2, as we noted at the beginning. Okay, for the AND rule, probability roll double sixes with 2 dice. Okay, I'm just doing rule 1, rule 2, rule 3. Okay, that's going to be probability of 6 on the first and 6 on the second. That would be a 6/6. This is probability of 6 on the first. In the AND rule, do I have dependents? Well, these are 2 dice which we know are not dependent, so I can simply go probability of 6 on the second. And we know that that is probability of 1/6 times 1/6, which is 1 out of 36. If you weren't sure if there was dependence or not, you could still put 6 on the second given 6 on the first, and you'd work out, oh yeah, this probability turns out to be 1/6. So there would be no loss of taking that extra step. Okay, now let's consider 2 dice problems. Things get a little bit more complicated. Okay, what's the probability that x equals 7? What's x? In the 2 dice problem, the random variable x is the sum of the faces of the 2 dice. That's what we're going to use. And so what's the probability that x equals 7? Well, let's see. How many ways could it equal 7? Let's write them out here. I could have probability of 1 and a 6, or we could get the 2 and a 5, or we could also get the 3 and 4. That's going to cover it, but I could also get a 4 on my first roll, followed by a 3, or I could get a 5 on that first roll, followed by a 2, or I could get a 6 on the first roll, followed by the 1. These are all the ways that would give me a 7. Now, that's a probability of 1 and 6. Using the AND rule, it's probability of 1 times 6. ORs, for the mutually exclusive case, is 1/6 mutually exclusive from the 2, 5. Well, let's see. Is that mutually exclusive from 1/6? Absolutely. They cannot occur together, so I can simply add them up. There's no need to subtract anything. Probability of 2 times probability of 5. And frankly, I would not want you to do so much work. That's why I'm writing this whole bloody thing out. This is crazy. It's like when the apostle says, am I insane? I will go on to boast of things in the heavenlies. And he's just going off. This is not the typical thing you want to do. 1 is 1/6, 6 is 1/6, and you know that these guys are all going to be 1 out of 36, and so there's 6 cases of 1 out of 36, which is going to be 6 out of 36, or 1/6. Wow, that's crazy. Okay, not something that we need to do. Just because this is so common, I want to show you a shortcut for it. This table has, if you roll a 1 on the first, 1 on the second, then you get a 2. If you roll a 6 on the first, a 1 on the second, you get a 7. 5 on the first, 2 on the second, you get a 7. And so we can see there are 6 ways to get a 7, and each entry is equally likely which gives us a 1 out of 36 probability for every entry. So by direct observation, we could also say this event is 6 out of 36. Now, what's the probability that x is greater than or equal to 9? You're rolling Monopoly, and we want to get greater than 9. Okay, let's say, well, 1, 2, 3, 4. Okay, 5, 6, 7, 8, 9, and 10. Looks like there's 10 different ways to get greater than or equal to 9. And so we're done. Okay, there's a lot of symmetry in the chart. It's worth taking a look at. Now, let's do some cards. Okay, we've already talked about the deck, so we got that. Well, looking at probability rules 1, 2, and 3. Rule 1 is just the sum of the complements, so diamonds, hearts, clubs, and spades. We know that each of those is going to be 13 out of 52, okay? So those have to add up to 1, or 52 out of 52. So rule 1 is pretty intuitive, and that's, we got that. Now how about 5 and heart? What's being got at there is a card that has events both 5 and heart. Okay, how many of those are there? We know that that's unique. There's only one such card. So we're going to go ahead and write 1 out of 52. Okay, but would it work using the rules? Let's give it a try. 5 and heart, using the rules, that would be probability of 5 times probability of heart given 5. Given 5, let's just use the bar. Well, we know that there are 4 out of 52 5s, and if you have a 5, okay, so I'm going to have the heart 5, I'm going to have the spade 5, and so on. Just the 4 5s. It's given that we have one of those. What's the probability that there's a heart? Well, out of those 4 possible 5s, only one of them is the heart, and so I would still wind up with 4 out of 52. So the rules are consistent. Thank you, Lord. Colossians 1, 16, 17. Probability of a 5 or heart, that's going to be probability of 5 plus probability of hearts, but they are not mutually exclusive. There are some cards which are both 5 and hearts. That's this guy right there. That is the 5 of hearts, or the 5 and hearts. So we have to take that one off when I do my calculation. And so the 5, we know there's 4 out of 52. The hearts, there are 13 out of 52. And so we're going to just subtract off that 1 5 of hearts to get us 16 out of 52 hearts. Okay, last up. What's the probability of drawing a 5 on the first draw and a 4 on the second draw? So now we're considering 2 card cases. So this is not the simple case, it's 2 draws, and we assume no replacement. So 5 on the first, it's an and, which means we multiply. We're going to do 4 on the second draw, but it's given that there's already a 5, so we know we have 4 out of 52, and then given that we've drawn a 5 out, we're now missing one of those cards in the deck, but there's still 4 4s, so that's a sufficient answer. Could be simplified, but in probability, it's nice to leave things plain. Lastly, what's the probability of a 5 on the first draw and a heart on the second draw? This is a little bit more complicated, so let's take note. 5 first, heart second. That's going to be probability of a 5 on the first times the probability of a heart on second given a 5. Now, if we think about this for a little bit, this probability, heart on the second, depends upon whether this 5 was a heart or not. Therefore, I'm going to break that into 2 cases, and Whitlock Schluter talks about doing tree diagrams, breaking into multiple cases. And I'm not too into that, but if that helps you, then here we're going to go ahead and do that. We can take this as probability of heart on the second given 5 of hearts. Let's just say 5 of hearts. And I'm going to have to erase this. I didn't get this done too well. Let's do a probability of a heart on the second given 5 of not hearts, so 5 of heart complement. Well, given that I've got a 5 of hearts, what's the probability that I'm going to draw a heart out? Now, there's only 51 cards left in the deck, but 12 of them are hearts. Whereas over here, there are 51 cards in the deck left, but we know that 13 of them are hearts. Now, we're going to take the first component here, probability of 5 on the first, and if we do probability of 5 of hearts, and we can break that into probability of 5 of heart complement. 5 of hearts, we already know there's 1 of those in the deck. 5 of not hearts, there's 3 of those in the deck. Now, trying to combine all these results, let's see, do this on the side here. Probability of 5 on the first and the heart on the second is 1 out of 52, that's 5 of hearts, times 12 out of 51, that's heart on the second given the 5 of hearts, plus the 3 out of 52, this is the non-heart, times 13 out of 51. And I'm just going to do the math on this one because it's interesting. 3 times 13 is 39, plus 12 is 51, over 52 times 51, same denominator, which turns out to be 1 out of 52, which is very, very interesting. And that concludes the basic examples. Okay, let's move to the last example. Canaanite State College doing a study to determine if putting a fee on course schedule changes has an effect on the number of changes students make. Fancy that. 400 total students in the study, and this is based upon something Biola did a number of years ago. All right, we have a two-way table here, or a contingency table. And so the probabilities from these tables are relatively straightforward, but I want to go through it. So probability of no change, let's call that no change, change, no fee, fee. Okay, so no change, as I look at it, I've got 260 no changes out of the total 400. And that just gives it to me straight. We can also write that in a decimal form, which might be nice to do, 0.65. Okay. Changes then are 140 over the 400, which is going to be 0.35. Now, using rule 1, if you add those together, better add up to 100%. They're complements. That's the sum of the complements rule. Okay, now let's go after rule 3. I want to do no change and phi. So it's not simply the sum of no change. I said and, or. It's not the sum of no change or phi. Okay? Rather, what we have to do is take the no change plus the phi, and we have to subtract off those which are both no change and phi. I want to be explicit about this. No change in phi, let's go ahead and grab a different color. No change is this column, phi is this row, so the no change and phi is that group right there. Okay, that's no change and phi. So going back, it's 135 out of 400 minus 135 out of 400. So we do the math on that. We've got 0.8125. Okay, lastly, I'd like to write out no change given phi. So for this one, we have no change consists of a group of only 260 students. The phi group consists of these 200 students, and so if we want probability of no change given phi, then there's 200 students in the phi group. There's 135 students who have made no change, so we've got 135 out of 200. That goes here. Okay, which is 0.675. Now, phi and no change, using the product rule, we have probability of phi times probability of no change. However, if no change and phi are dependent, then we're going to have to use the conditioning here. Whether they are or not, we would need to check. So, probability of phi, we have okay, phi is 200 out of 400, and no change given phi we just completed, which was 135 out of 200. We have a little cancellation here, 135 out of 400. And I want to note that this phi and no change is an observation that we could make directly up here. No change in phi, we already said, was 135 out of 400. The rules are consistent.